Now, multiple bonds. Sometimes elements can share more than one pair of electrons between two atoms. If we were to look at oxygen, for example, oxygen has 6 valence electrons. If you look at another oxygen, also has 6 valence electrons. So, this unpaired electron can pair up with the other unpaired electron, and these two can also pair up. I like to think of it as you take 2 electrons to form one bond. So if I redraw this, I can draw it with all the shared electrons in the center, and then the unshared electrons outside. Notice how there are 2 pairs on one atom that aren't involved in the bond. So this becomes a double bond. Nitrogen, on the other hand, is this. Nitrogen has 5 valence electrons. So each of those unpaired can pair up. So we would put 6 electrons that are being shared. 1, 2, 3, 4, 5, 6 in the center, with only a single pair on each nitrogen not being shared. Again, we can go around, and if we circle the shared with the unshared together, that has 8, and this has 8, which now has a triple bond. One thing to consider is that when atoms are closer together, when the distance between the 2 nuclei of bonded atoms are closer to one another, then that strength of the bond becomes greater. So if I were to take nitrogen, if, for instance, a nitrogen only had a single bond between them, this would be a distance of 1.47 angstroms. A double bond has a distance of 1.24 angstroms. A triple bond has a distance of 1.10 angstroms. So this bond is the strongest. And the nuclei, if I were to just sort of draw, so maybe these nuclei might be that far apart, these nuclei slightly closer, these nuclei the closest to each other. So this bond will be harder to break apart. However, even though overall, like it's hard to get through all 3 of those bonds, this also is the most reactive or unstable. Because one of these, the third bond, is going to be much more reactive than, say, a single bond by itself. So now we've seen how atoms can get a full valence shell by sharing. However, this sharing is not always equal, and that leads to what we call polarity, which is unequal sharing. So if you were to imagine 2 twins fighting over candy, so these are 2 kids that are completely identical in terms of strength, and let's say they're fighting over a pile of candy, probably that distribution of candy is going to be pretty even. However, if you had a bigger kid versus a smaller kid, probably it's going to be uneven distribution of candy. The same can be said if you have atoms that are the same and atoms that are different. For instance, if you have oxygen and oxygen sharing electrons with each other, so these 4 electrons, then the distribution of electrons around both atoms should be even. However, when we have 2 different elements, for instance, hydrogen and chlorine, sharing could be unequal. The reason why is if we look back to electronegativity. What we should already know is that if we have a nucleus with more protons and a smaller radius, then we should see greater electronegativity. And what electronegativity is kind of an electron greediness, or it's the strength of pull an element has on electrons, not only its own electrons, but electrons that are not its own. So if something has a greater electronegativity, it's going to have a greater pull on electrons. So if we are to look at hydrogen and chlorine, chlorine has 17 protons in its nucleus. Hydrogen has a measly 1 proton. Protons again are positive, but electrons are negative. So there's a stronger pull by these 17 protons on these 2 shared electrons than there is by this 1 single proton over here. So what happens is that these electrons spend more time with chlorine. Another way you might think about it is if we have something that is even sharing, you could think about it as joint custody, where parents get their children an equal amount of time, 50% of the time, each parent. Unequal sharing of polarity is kind of like one parent gets the kids most of the time, and the other gets them every other weekend and Wednesdays. So in this case, chlorine would get the electrons most every other day. Hydrogen just gets to see the electrons every other weekend and Wednesdays. So if we were to go further with this, since there's unequal sharing of electrons, that means there's an unequal charge distribution on the atoms in that molecule. So if we take hydrogen again and chlorine again, then we can say that since the electrons hang out more often with chlorine, it has a partial negative charge. And since the electrons hang out less often with hydrogen, it has a partial positive charge. If we think back to sodium and chlorine, remember that sodium totally gave its electron over to chlorine. So this is like sole custody. Chlorine now has sole custody of that electron, so it gets a whole negative charge, and sodium gets a whole positive charge because it has one less negative electron. So how do we tell if an element is going to be polar, nonpolar, or ionic? And then how do we tell where the electrons are going to hang out? Where will be the partial positive charge and the partial negative charge? Well, we do this by looking at values for electronegativity. In this case, if we have oxygen paired with oxygen, well, one oxygen has an electronegativity of 3.5. The other oxygen has an electronegativity also of 3.5. So to compare them, all we do is find the difference. So if we take 3.5 minus 3.5, we have a difference of 0. So this is what we call a non-polar molecule, which means there's equal sharing. There's an equal charge distribution. Let's look at water. So when we calculate this difference in electronegativities, we just concentrate on one bond. So in this case, we'll look at the relationship between one hydrogen and one oxygen. Oxygen, again, has that electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So if I take 3.5 minus 2.1, I have an electronegativity difference of 1.4. So this 1.4 tells me that this is polar. This means that there is unequal sharing and an unequal charge distribution. So again, I look back to this electronegativity. Well, 3.5 is bigger than 2.1. So that means the electrons hang out with oxygen more often. Electrons are negative, so oxygen will have a partial negative charge. Since the electrons hang out more often with oxygen, they hang out less often with hydrogen. Hydrogen will have a partial positive charge. Finally, if we look at lithium oxide, so lithium has an electronegativity of 1.0. Oxygen still has an electronegativity of 3.5. So 3.5 minus 2.5, this tells us our compound here is ionic. This means it's not only unequal sharing, we actually have electron transfer going on. So what happens instead is that between this lithium and this oxygen, lithium has a positive charge. Since oxygen got both of those electrons, it has a 2 negative charge. So the cutoff point between whether something is polar or ionic is 1.7. So in this case, the 1.4 is smaller than that 1.7, and 2.5 is greater than the 1.7. And if we have two things that are completely equal so that we have a difference of 0, then we have something that is non-polar. So now that we know that there's this unequal distribution of charges and that we can also end up with partial positives and partial negatives, we also